So this will be our last lecture on this chapter, but we're going to continue talking about acids and bases, and we're going to look at how they affect the environment we live in, among other things. One thing that we want to talk about is acid rain. Now, you might have heard of acid rain before. It is a problem that's more prevalent in heavily industrialized areas. Particularly in the northeastern United States. That is one area which has long had struggles with acid rain. And basically, acid rain is caused by burning of fossil fuels. You burn coal or diesel or oil, and one of the byproducts of that process is sulfur dioxide. And so you can see sulfur dioxide here, SO2. And what happens is sulfur dioxide gets released into the atmosphere when these things are burned. And it combines with the oxygen in the air, and it forms a chemical called sulfur trioxide. Tri means three, so this is sulfur trioxide. Now, that chemical then mixes with the water vapor in the air. So you have the sulfur trioxide mixing with the water, and that forms H2SO4. Which is sulfuric acid. And by the way, just to remind you, these letters in the parentheses, the G, that tells you that this is in the gaseous state. So you've got the sulfur dioxide gas mixing with the oxygen gas, forming sulfur trioxide gas. That mixes with the water vapor, which is in a liquid state and in the air, and then that forms the sulfuric acid, which is in aqueous solution. That means the sulfuric acid is dissolved in the water vapor. And so what happens is the water in the atmosphere becomes more acidic, and when that rain falls on things, it causes them to corrode. It makes it more difficult to grow plants. It creates an environment where plants don't flourish as well, and it can cause a lot of industrial damage and a lot of other kinds of damage in the area. So for a long time, companies have been working on ways of reducing this kind of pollution to prevent the worst effects of acid rain. When people think about air pollution, they often think about the sort of things that go in the air that make it harder to breathe, that maybe exacerbate asthma and things like that. And those kinds of things are bad too. But this is just another example of how pollution can cause damage to our environment and make our lives harder. So we work to reduce pollution as a society because that provides health benefits, it provides benefits that are financial benefits, and pretty much every other kind of benefit. So this is also an example of how chemistry affects our daily lives, because understanding these chemical processes let us understand different kinds of pollution and how we can maybe mitigate them or make them not as effective. Now, we talked about acid rain, and I mentioned that it, in the United States at least, primarily affects the northeastern part of the country. There are other places in the United States that are heavily industrialized that don't see it as much of a problem. And one of the reasons for that is the environment in which the acid rain occurs. So we've talked about how the water in the air can become made more acidic, and then when it falls as rain, it goes into, say, for example, a lake. And depending on what is underneath the lake, you can have certain chemical reactions. So in some parts of the country, there's a lot of calcium carbonate in the ground, and so the water in the lake becomes more acidified, but the ground underneath the water has this calcium carbonate. And so what happens is you get these hydronium ions, they combine with the calcium carbonate, and they produce compounds that are effectively neutralized. And so the acid rain gets less of an impact because simply falling into these lakes or falling into regions where they have this calcium carbonate, it gets neutralized, and so the acid is less destructive. But if you're in a place that, for example, has not calcium carbonate but some other kind of structure like granite, the acid rain falls in the lake, and the concentration of the hydronium ions just gets higher and higher, and the whole lake can become acidic. And so that can affect the plants that feed on the water in the lake. It can affect the wildlife that uses the lake. And of course, it can cause all kinds of other problems as well. And so that's one of the things that chemistry can inform us, is that, so, it was a question, why is acid rain so much more of a problem in this area than that area? We can look to the chemistry to understand that, which is pretty cool if you think about it. Now, you've probably heard that the release of carbon dioxide into the air is a contributing factor to global warming. Now, we're not going to talk about global warming in this lecture, but it's something that a lot of people are aware about because it's a very, very serious problem. And it's caused by human activity, from burning fossil fuels for energy to our agricultural processes to many, many other areas in industrialized human society. The byproduct of our living is that we release a lot of carbon dioxide into the air. But when you look at the concentration of carbon dioxide in the air, it actually is less than you would perhaps predict it should be based on just how much carbon dioxide we're putting into the air every year. And part of that is because 70% of the Earth's surface is covered in water, and all of our oceans together form a tremendous sink for carbon dioxide. In other words, our oceans absorb huge amounts of carbon dioxide. So what does that mean, that our oceans absorb carbon dioxide? Well, it's, again, through chemistry. In this slide, we see a specific chemical reaction. We have carbon dioxide gas, which is interacting with liquid water, and it forms this chemical H2CO3. And of course, again, that AQ means that chemical is dissolved in the water, in this case, the water of the oceans. And this chemical is called carbonic acid. And so what happens is that the chemical process removes the carbon dioxide and it dissolves it into the oceans, which creates this new chemical, the carbonic acid. Now, our oceans have other things dissolved in them that make them more alkaline or more basic. Now, you might think that, great, so we can produce all this carbon dioxide and it'll just get absorbed by the oceans. But actually, we're overwhelming the ocean's abilities to absorb the carbon dioxide that we're putting in the air. We put so much carbon dioxide in the air, the atmospheric concentrations of carbon dioxide have been rising. And of course, this results in global warming and other problems, but we're going to focus on just the chemistry of these reactions in this chapter, and we'll talk about global warming later on. Now, the next thing that we're going to talk about is what are called oxidation reduction reactions. Now, we've previously in this chapter been talking about acid-base reactions. And so an acid-base reaction is a reaction where a proton is transferred from one molecule to another molecule. Or in other words, you have a gain or a loss of a proton. That is an acid-base reaction. What we're going to talk about next is a oxidation reduction reaction. Now, if an acid-base reaction is a transfer of a proton, what do you think an oxidation reduction reaction might be? What kind of transfer might it involve? And so this is what we call it. It's an oxidation reduction reaction, and it involves a transfer of electron. Now, when you have a loss of an electron, that's called an oxidation reaction. So here's an example of that. We have two neutral sodium atoms, and those two neutral sodium atoms lose two electrons, and so they become two positive sodium ions. Remember, Na is the chemical symbol for sodium. So we have two sodium ions and two electrons. Now note, here, this is a neutral chemical. It's just sodium, and for every proton, there's an electron. But when I take away some of the electrons, I take away some of those negative charges, I'm left with positively charged ions, but the total charge remains neutral. Just, always be aware of that charge can never be created or destroyed. It can only be moved around. Now, if an oxidation is the loss of an electron, as we've seen in this kind of reaction, a reduction is what we call a situation where there's a gain of an electron. And so here's an example where we have a neutral chlorine molecule and it picks up 2 electrons, so it gains 2 electrons, and then it becomes 2 negative chlorine atoms. So it's gained 2 negative charges. Now, to remember that an oxidation is a loss and a reduction is a gain, we have this acronym here, Leo the lion goes grrr. I don't think that really is what a lion sounds like, but we'll just go with that for our mnemonic to help us remember that. And so Leo the lion goes grrr. So Leo, loss of electron, is oxidation. And then grrr, gain of electron, is a reduction. And so Leo goes grrr. That'll help you maybe remember which is which. Now, it's probably worth noting that, these kind of reactions are dependent on each other because the sodium's not just going to be losing these electrons willy-nilly. They're only going to lose them if there's somewhere for them to go. So, for example, there happens to be some chlorine gas nearby that these electrons could be picked up by. And so just beware that, basically this is half of a reaction and this is half of a reaction, and you can put them together for the whole reaction. And so, for example, we can have 2 sodium atoms and a chlorine molecule, which is made of 2 chlorine atoms. They combine together and make 2 sodium ions and 2 chlorine ions. And so, let's remember we have our mnemonic here. Leo went grrr. Let's use this to examine this reaction a little bit. So let's consider the sodium. It ends up positive. So does that mean it gained an electron or lost an electron? So obviously, if it's left with a positive charge, it means the negative has been taken away. So it's lost an electron. And so lose an electron is an oxidation. So we can say that the sodium was oxidized in this reaction. In other words, the chlorine is acting as an oxidizing agent to oxidize the sodium. And remember, when we say oxidize, that just means that we have lost an electron. That's an oxidation. Now, at the same time the sodium loses electrons, the chlorine is gaining an electron. And so that is called a reduction because gain electron is a reduction. So the chlorine is reduced by the sodium. The sodium is the reducing agent. And that's just a lot of different ways of saying the same thing. Mainly what I need you to know is that when you lose an electron, it's an oxidation reaction, and when you gain an electron, it's a reduction reaction. Now, we've talked about electronegativity and how some atoms will more strongly hold on to their electrons than other atoms. And so that means that some atoms are better at gaining electrons and some atoms are better at losing electrons. Now, if we look at the periodic table, that can kind of give us a clue. Now, we have this purple column over there, and we know those are the noble gases, things like neon and argon. They don't interact with anything. They keep to themselves. They're loners. They just hang out by themselves. They don't join together and form compounds with the other kids. Now, if you look at the rest of the periodic table, when you're in the upper right-hand portion of the table, those elements have a tendency to gain electrons. Whereas if you're on the lower left portion of the table, those elements have a tendency to lose electrons. And so The blue ones are more likely to be an oxidizing agent, that is, they're more likely to be reduced, i.e., they're more likely to gain electrons, whereas if you're in this portion of the periodic table, you're more likely to lose an electron or be oxidized. Now, there are different ways that you can have oxidation and reduction. The main way that we've been talking about is gaining or losing electrons. It's not always obvious when you look at a chemical reaction whether you're having an oxidation or a reduction. And so there are some clues that can help chemists determine whether or not one process or the other is occurring. Now, obviously, something like sodium chloride being formed, that is one where you have ions which have clearly gained or lost electrons. And it's obvious because if you lose an electron, you've had an oxidation. If you gain an electron, you've had a reduction. But there are some other clues that chemists can use to determine whether or not you have an oxidation or reduction. And so if in a reaction that something gains oxygen or if it loses hydrogen, those are both indicative of oxidation reactions. And of course, the reverse is true. If it loses oxygen or if it gains hydrogen, that's indicative of a reduction reaction. So the main point is it's not just whether you're losing individual electrons or gaining individual electrons. There are other ways that you can have these oxidation reduction reactions. But in each case, what happens is the ionic state becomes more positive in an oxidation and the ionic state becomes more negative in a reduction. So let's look at the following reaction. We have iodine, which is combined with bromine ion, and it forms an iodine ion and a bromine molecule. And so in this situation, which element is oxidized and which element is reduced? And so let's think about it. We have our mnemonic, Leo goes Gur, and so we know the loss of an electron is an oxidation. So which one of these guys loses an electron? Well, the bromine has an extra negative charge, and then it doesn't have an extra negative charge, so it has lost a negative charge. And so a loss of an electron is an oxidation. Now, the iodine, on the other hand, is neutral here. It's negatively charged over here, so it's gained electrons, and so a gain of an electron is a reduction. So the iodine is reduced and the bromine is oxidized. And so that suggests that B is our answer. So we can circle our answer there. Now, another thing that is very useful is that these kinds of oxidation reduction reactions can result in electric currents. And electric currents can power everything from your cell phone to a clock to a radio to the ignition in your car. There are many, many different things where electric currents are needed, and these kinds of reactions can provide them. Specifically, we're going to see how these kinds of things are used in batteries and fuel cells. So we want to look at how these kinds of oxidation reduction reactions can lead to a flow of current. So as an example, iron atoms, they're better reducing agents than copper ions. So if you take a piece of iron metal and a solution containing copper ions and you put them in contact with each other, the electrons are going to flow from the iron to the copper because you end up with an oxidation of the iron atoms and reduction of the copper ions. Now, if the elemental iron and copper ions are in physical contact, this reaction can happen directly. But if you can put them in a separate container that is bridged by a conducting wire, the electrons can flow from the iron through the water to the copper, where that oxidation reduction reaction can occur, and then you get a current. The problem is, as the charge flows from one to the other, you get a buildup of charges in each solution. This container would build up a big positive charge, and this one would build up a big negative charge. And of course, we know that negative charges here are going to repel any electrons that want to flow down this wire, and that's going to stop the flow of current. So you'll get current flowing for a little bit, but then essentially the current stops. So how do we fix that? We provide a path for those ions that are building up in these solutions to move around. And so one way to do that is to create what's called a salt bridge. So here we have the same setup, but we have a sodium nitrate salt bridge here, and there are some porous plugs here, so they're porous so that these things can move from one to the other. And what you'll have is you have the buildup of positive ions over here will tend to flow that way. The buildup of negative ions over here will tend to flow that way. And so it creates a redistribution that allows the current to keep flowing. And this is the basic principle about how a battery works. So you have this chemical reaction, which is creating an electrical current. Now, another way of doing this is with what's called a dry cell. And so you don't want to have, beakers with liquids in them that you have to haul around to power your clock radio. That would just be messy. And so a dry cell, instead of using a liquid, it uses a paste. So you have a graphite rod here. Graphite is a form of carbon, and it's immersed in a paste of some different chemicals. You can see the chemicals here that make up this paste. And then there's a zinc cup. Now, graphite is a good conductor of electricity, and the chemicals in this paste get reduced. And so you can see a reduction reaction here. The 2NH4 plus the 2 electrons make 2NH3 plus hydrogen. And this represents a reduction, because this guy gains electrons and is reduced. And just FYI, and by the way, any material that conducts electrons into or out of a medium where electrochemical reactions are occurring, that material is called an electrode. And the electrode where chemicals are being reduced, that is, they're gaining electrons, that's called a cathode. And that means the cathode is always going to end up being positive. Now, the electrons that are gained by the chemicals at the cathode, they originate at the other electrode, which is called the anode. And that's where the chemicals are being oxidized, i.e., where electrons are being lost. And so in this kind of battery, that's going to happen on this zinc cup that contains the thing. So the zinc is going to have an oxidation given by this reaction that you can see here. In other words, the zinc is losing electrons, that's the oxidation, and becoming a positive ion. So we have the cathode here, which is positively charged, and we have the anode, which is negatively charged. And so those electrons are going to be, so the electrons here at this part of the battery are going to be attracted to the positive charges here, and so that's going to generate current as the charges will flow down the wire. And then, of course, you can light your light bulb or power your alarm clock or your cell phone or whatever it is that you're using with the electricity produced by these chemical reactions. So just to sum up, the positive electrode is the cathode, and that's where a reduction reaction occurs. The negative electrode is the anode, and that's where an oxidation reaction occurs. Now, we were just talking about what were called dry cell batteries. The very first battery I showed you with the chemicals in the beakers, they would be, I guess you would call that a wet cell. The dry cell is with the paste. But there are other kinds of batteries too. There are what are called alkaline batteries. And then, of course, there are rechargeable batteries. You don't want to have to put a new battery in your cell phone every day. So our cell phones actually use rechargeable batteries rather than the disposable batteries that we've talked about previously. And by the way, they're disposable because, those chemical reactions are involving things getting broken up or dissolved, and eventually they just sort of, they all get used up. So that's why they're disposable. But the rechargeable batteries, you can reverse the reaction and recharge them, which is, of course, very useful for something like a cell phone. Now, another application of this is what's called a fuel cell. And a fuel cell is a device that converts chemical energy of a fuel into electrical energy. And they're actually the most efficient way of generating electricity from this type of process. And in this figure, we see a schematic of a hydrogen-oxygen fuel cell. So in this cell, you can see there are a couple of places that are input. So there's an input right here where we can put in hydrogen fuel. And there's an input here where we can put in oxygen and water vapor. These inputs are going into these compartments that are separated by these porous electrodes. You can see these porous electrodes. So we're inputting our hydrogen fuel here, and it comes in contact with this electron and it becomes oxidized. That is, it loses electrons. And so these electrons then flow from this electrode, which is going to be the anode, and it'll flow through the light bulb, and then it comes over here, and those electrons meet up with the oxygen. And so we can see these reactions here. I've got the hydrogen gas meets up with these hydroxide ions in this electrode, and they form water, actually water vapor. So it's pretty energetic. It's enough to be converted into steam. That's what the little G tells me. This is in a gaseous state, plus some electrons. These electrons can flow down the wire, and then they meet up with the oxygen. And that creates a reduction reaction. So here we have an oxidation reaction that creates the electrons. The electrons flow down the wire. They power the light bulb or the cell phone or the clock or the car or whatever it is. They come out over here and they meet up with the oxygen and they get reduced. And so this is, again, a way that these oxidation and reduction reactions can create electrical currents. Now, there's a lot of research currently being done on fuel cells, and a lot of it is for cars, because this is a very efficient way of using electricity, but there's a couple of problems. One is the fuel. Hydrogen doesn't generally exist by itself on Earth. You have to extract it from other things, and that takes energy. And then you have to store it, and it's, storing enough hydrogen to power this for something like a car is something that is an engineering challenge, but a lot of really smart people are working on it. And some people are actually working on using this idea to make cell phone batteries. And so from the large scale to the small scale, this technology could become very important in the future. Now, the next topic that we're going to talk about, and I know this is a really long lecture, but we're getting towards the end. We're going to talk about something called electrolysis. Electrolysis uses electrical energy to produce a chemical change. Some examples of this include recharging your car battery, and it's a process that's used for purifying certain types of metal ores. One of the most common elements on the earth is aluminum. It's a lightweight, strong metal, and it's used in so many things today. But that wasn't always the case. It used to be that pure aluminum was more rare than gold, because while the earth has unbelievable amounts of aluminum, it's all bound in a chemical called bauxite. And so extracting the aluminum from the bauxite used to be an incredibly expensive process until a couple of guys, one named Charles Hall and the other named Paul Héroult, independently discovered a process of using electrolysis to extract aluminum from bauxite by making use of these oxidation reduction reactions. Now, you can see from this figure, this process is pretty complicated. I think it's a little bit beyond, what I want to expect you to be able to talk about. But the main thing is that you just understand that this process of electrolysis can actually create chemical changes that are very useful. Aluminum now is one of the cheapest metals that you can get. It used to be more expensive than gold, but because of this process of electrolysis, we can extract aluminum from the earth and use it for all the things that we use aluminum for. So the final topics in this chapter that we want to talk about are corrosion and combustion. And these are two very, very important processes. Corrosion is the process by which a metal deteriorates through an oxidation reduction reaction. So let's take a common one that is a problem for a lot of people. So let's say you have a fence that's made out of iron. And so there's a reaction that occurs when iron interacts with oxygen and water. Guess what? There's oxygen in the air. There's water vapor in the air. So the reaction that I'm talking about is if you have 4 iron, and the chemical symbol for iron is Fe. That comes from Latin. But 4 iron plus 3 oxygen molecules, that's 3O2, plus 3 water molecules. And what does that yield? It yields 2 iron oxide and weakly bound water molecules. And so this is what we call rust. So this is a principle that comes from what we call corrosion. The iron is corroded by the rust. And of course, this is a big problem. And so that's why if you have iron, you don't want to get it wet and leave it wet, because that's going to accelerate this process of rusting. One of the ways that we can protect iron from rust is to coat it with something else. And so very commonly, something like a nail will be coated with zinc, because the zinc will oxidize, but it'll be a very thin layer of zinc oxide around the nail, and that protects the iron underneath. You can see the same thing in this picture of the ship. There are strips of zinc, which is performing the same process. Basically, the zinc tends to oxidize before the iron, and that forces the iron to accept electrons. And the long and the short of it is that this process prevents the iron from rusting. So that's kind of a neat trick that we learned from chemistry. And the last thing we're going to talk about is combustion. Now, combustion is an oxidation reduction reaction between a non-metallic material, wood is the classic example, and oxygen. And so here we see a schematic showing actually the burning of methane, which is a chemical fuel. And so we have methane, a methane molecule combining with oxygen, and we can actually write down the reaction. So we have CH4, which is methane. It combines with oxygen, and it creates a chemical reaction that produces carbon dioxide plus water and then energy. That means this is an exothermic reaction. Remember, we talked about exothermic reactions or chemical reactions that release energy. And in this particular reaction, it happens very, very fast, and so it releases a lot of energy. And so this is why we can burn methane, and you can create a flame from the methane. That's that release of heat and light. That's the energy being released in that process through this chemical reaction. And of course, the byproduct of this reaction is carbon dioxide. And so as we talk about burning fossil fuels and how that releases carbon dioxide into the air, it comes from these kinds of chemical reactions. And so finally, we are at the end of this lecture. Hopefully you found it interesting and informative. And so this will bring this lecture to an end.